Hey, this is Alex from Gretel. Today we're going to walk through an end-to-end example of creating fully anonymized synthetic patient data that can be used for AI, ML, or analytics use cases. This data out of the box will be compatible with GDPR, HIPAA, and other, even the most stringent anonymization requirements. So let's go ahead and dive in. We'll start with a notebook here. In this example, we're actually loading the data up from BigQuery. So we have the BigFrames SDK that we're using. I'm going to click Run All, and we'll walk through what's happening here. So the first thing it's doing is installing required packages. We can also do this through the Gretel console. We're using the notebook here because it allows us to dive in a level deeper. And we're going to start with de-identifying the data. So the very first thing that we'll do is first load the data set. The next step will be to create a simple policy that will remove the known PII inside of the data. The reason we do that is we don't want the model to memorize or ever have seen access to specific things like patient records, patient IDs, things like that it doesn't really need. So let's go ahead and get our API key. We can grab that from Gretel. That is easily fits within the free tier. So if you don't have a Gretel account, you can just sign up at Gretel AI and run through. The next step here will be loading up from the BigQuery public datasets. We'll be loading up this sample patient data. So this is a synthetic patient data set that we can use. But it mimics the complexities you see in real-world patient data. So we have embedded JSON fields, we have time series components. It's a really difficult test, and it really shows off the flexibility of Gretel's multimodal model, so including the navigator fine-tuning. Let's let it load here. So here we see a preview, first preview of the data set we'll be working with. You see patient IDs in here, you see first names and last names. We're going to remove these first. While the model, the underlying model we're using is a transformer-based model, and it's unlikely to memorize or replay these exactly, we don't want to take that chance. So let's go ahead and remove that. The synthetic model is going to help us with a couple things. One, it'll make sure that none of the other attributes here, this combination of race and height and weight, or things that you might note, like an event date, like a time that someone may have stopped by a hospital, would end up being identifying for these users. So this is a really critical component of anonymizing data. You have to go beyond just removing, for the example, the known PII identifiers. This is where things get really fun. You can't see all of the data here inside of this data frame view, but you have both this mixture of like categorical data, like what clinic that you came into or who the doctor was you're working with, mixed with free text data. So you have doctor's notes, we have details which are embedded in JSON, we have occasional nulls. This really kind of mimics what you're going to see if you're working with, for example, Epic EHR medical records. For this first step, first thing we're going to do is we're going to use the Transform V2 service. So this is a data pre-processing and post-processing service from Gretel that allows you to quickly make changes to even very large documents. So what we're going to do here is create a schema, and we're going to tell transforms about the changes we want to make to our data set. The columns we called out here are this patient ID, the first name, and last name. So let's go ahead and just take care of those first. We'll let the synthetic model handle anonymization for the rest of the data. So what we're going to do here is we're going to create a policy that for a patient ID is going to take that patient ID and hash it. And then we don't want the full like mega hash. You could use it if you wanted to. Here we truncated it down to 10 characters, so it's just easier to look at. You still have very low chance of any type of collision happening or anything like that. So very safe to work with there. Next, on the first name, what we're going to do here is we're going to do something a little bit fancy. On the first name field, we are going to create, we expose any of the Python faker libraries. So you can fake, we're going to use the first name generator and female if the gender or sex of the patient is female inside the data set. So it's going to create a more realistic transformation of data. Still, kind of fake names being put in here. One of the other cool things about Gretel transforms is by default, it does what we call like deterministic faking, which means every single time you come across Aisha or Antonio, it will be transformed into the exact same synthetic value. You can change that using the seed, which you can pass in as well. So, but the neat thing is that the patient name will be preserved all the way through the process. We're not going to do anything fancy with the last name, so we're just going to deterministically fake it again. So this is the first step where we just de-identify the data set. So simple data set here, you can see transforms is quite fast. It ripped through here, looked at the patient IDs, first names, last names. So these have been changed. Everything else right now is the same as what we saw before. Now we're going to train our model. The use case, presumably, for this data is that you might want to use it for analytics. You might want to use it for training some sort of recommendation engine, or seeing how long patients are inside the ER for, what the next logical step is. So analytics and preserving these deep correlations across these like different types of data is very important. That's why we built Navigator Fine-Tuning. So Navigator Fine-Tuning is a first of its kind model. It's a transformer-based architecture, so you could think of it as being like a ChatGPT type model. And it has the ability to learn to recreate the kind of complex types of data that we see inside of databases, data warehouses, and tables. So going beyond some sort of like statistical approach here, really it is learning the deep correlations as we'll see inside of the data. We've done some slight tweaks here to the configuration. So it'll work out of the box. You can just pass this to Navigator, but we want to help Navigator come to really the best possible solution. So let's take a look at the data and see what type of components that we have here to think about. You have patient data right here. You have a patient ID. So presumably there will be multiple patients inside of this data set. And a patient may have multiple visits to the, for example, the ER that we're looking at here. What we want to make sure we do, and this is really important with patient data, is to capture that patient progression. So from the initial analysis when they first come in one day to the next day where they have some sort of treatment or surgery to the post-doc follow-up, it's all very important that that's captured. So let's help our model see that. What we're going to do is we're going to pass it in the patient ID so it understands the concept of a person. And then we can, I think there's a couple here we could try. The next one is the event date, and that seems very obvious. It also looks like there's some sort of event ID here, which may be an incrementing thing per patient. I'm not sure. So what we're going to do for right now is just go with the event date. And so it's going to essentially tell the model, look at a patient and look at it in the order of an event date. When you create synthetic patients here, then it has this concept of what a patient is and what a time series progression is. So that'll really help the model. Hopefully, as we'll see here, I'll go through. You can see here what has happened is we've kicked off the job in Gretel. This spun up a container that is doing fine-tuning of the model on this data set, and it's going to use it to create another data set just like it. And then it will run a series of tests on that data set. So we call that the synthetic quality report. But we've passed in the de-identified, so we removed the patient, we faked the patient first name and last name and the patient ID. And it's going through and it's training on this. And as soon as it's done with that, it will go ahead and create a new synthetic data set. I don't think anyone wants to wait here for 20 minutes, so what I'm going to do is jump over to a model that I have already trained. So we'll go into Gretel, go to projects, look at our patient data demo, go to models. You can see here this first one is the data transformation. It happens quite quickly, so that data transformation was done in about 28 seconds. The fine-tuning of this data set here takes, and generation takes about 15 or 20 minutes. So we'll see here, actually got it. We go to the completed project this time, and let's see how long it took to run, about 25 minutes to run here. We can see here that it got a synthetic quality score of 89. So let's dive in, like, what does that mean? So I can dive in here, I can go ahead and take a look at activity, and I can see the entire model training process from, for example, the data that we passed in or preview the data that we passed in, to the synthetic model training, to the quality score that we have here at the end. So 89 sounds great. Let's dive in and look at the report, and then we'll look at the results and see if it meets our expectations. Looking at the patient data here, once again, we see pretty good score. We see the field distribution for the non-text fields here as well, matched up. And one of the first things that we do is we do a pairwise correlation. So we compare all of the data in the training data set versus the data that was sampled from the model after the model was trained. And we look for how well it learned and recreated the distributions or correlations in the data. So you can see it did quite well here. Here's the kind of helpful view. This is a subtraction of the two. And you can see on one, it looks like it could have done better on maintaining the correlation between the race and the last name. That could be an artifact of the data transformation that we did, where we changed the last names to someone randomized last names. So wouldn't worry about that. Next, let's look at the principal component analysis. This really helps us figure out if the model's overfitting on data. Did it like memorize? It's not going to memorize. In this case, we have things to make sure that it doesn't, but did it get like overly trained on the data? Should we reduce the training cycles? What we look for is similar distributions and patterns between the data. Looks very similar there. And then finally, you get this like last kind of like just look at the individual distributions per field. So the height of patients, the weight of patients, how well did it match here? And what we see, what looks like very good distributions were maintained from these synthetic patients, where none of these would match up to a real world patient, to the real world patient data that it was based on. So you see these distributions matching very closely. So that's very encouraging. Now let's go back, and for the final test, let's look at the synthetic data and say, did it meet our expectations for what we're looking for so far? So this would be the last step before you go into something like a downstream machine learning use case or analytics use case, a deep analytics use case. We're just going to eyeball the data. Click download results. Open this up. And what do we have? So what we have here, we have the patients being created. You could see the synthetic data matches the distribution of data that we taught it. So we taught it to create an 8-digit or whatever this is hash. It looks like these hashes were maintained by the model. So it went ahead, or 10-digit, went ahead and recreated these. Also, we have first names and last names. Other interesting things, since we told the model about a patient and about a time series distribution, you can see that here as well. So you see patients here. This is how we know the model really learned the time series components, which is really difficult sometimes for models to learn. Here we see patient progressions where we have Dustin Young. For example, we have 1, 2, 3, 4, 5, 6 records from Dustin Young. And what we're looking for here is for this to make sense in time order. So really kind of a spot test on our data. But here's Dustin. You see admission, diagnosis test, treatment, follow-up, symptoms, medical examinations. We made them in multiple times here, but you see these orders, and let's look at a couple other patients here, really happening in a logical progression where you see the dates increase. Sometimes things happen on the same day, and sometimes not, right? So here on Antonio, we've got several records here. We have a treatment. They came in for something. We have admission. Let's see if I read that correctly. Yes, admission, symptoms. So you see this kind of like logical progression of the time series components you would expect to see with a patient going in and out of a medical system. So very, very important that these things are maintained. So we see just looking at the data, what looks like a very good job, both maintaining the expected distributions and correlations, race, gender, and names, which is the table stakes, and then the really kind of difficult things, having symptoms that make sense, and continued progression and treatment through the system that's going to help your downstream model learn how to work with this data. We'll attach the notebook and the links below, and let us know if you have any questions. Thank you.